Hi, I am Shubhana Hemmati at Caltech IPAC, and in this video I'll talk about the Euclid AGN tutorial notebook. In this notebook we showcase a science use case of AGNs using Euclid Q1 data. By the end of the notebook you'll learn how to do a galaxy color manifold from Q1 MER multiband photometry using a self-organizing map. We project different AGNs selected with various methods onto this color manifold, and we compare them. We also query Q1 spectra for the AGNs and look at the H-alpha line measurements from SPE. I'm not going to read the notebook in detail to you in this video, and I will put in the link to the public GitHub page of where this notebook is currently hosted, and hopefully in the near future we'll change that link to the main IRSA tutorial of these AGNs. If you're interested in learning more about the method of looking at AGN selections on a SOM, you can refer to this paper by Sanjaripour et al. 2024, which studies a similar idea with galaxies of the MASTEF survey in the Candles field. And there is an in-prep work to do this with the Euclid Q1 data, part of what you see already in this video. The data that is used in this notebook, the catalog of AGNs, comes from the EC paper by Zatarin et al. 2025. The Q1 data that is released contains Euclid deep field north, south, and fornax, and to the wide depth. We also use the Euclid Q1 MER template with photometry, which includes both ancillary optical GRIZ bands as well as NISP, YJ, and H band. We'll query the photo Z from the MER photo Z catalog, and also physical parameters. We get H band. In the future, when the masses and other physical parameters are also measured, we will include those, and also the spectroscopy from SEER and H-alpha measurements from SPE. Okay, so we are limiting our redshift to 1.3 to 1.8. This is mostly to cover H-alpha in the red GRISM and to bound this notebook to a smaller subset. So in principle, there is no reason to limit this. You can measure the sum in any redshift bin that you're interested in for your science case. And we will use a 7-band photometry, so GRIZ plus YJH, and in the different fields in the deep Euclid deep field north, south, and fornax, sometimes we don't have the same GRIZ, so we choose the deepest one in each of them. Okay, so to talk about the workflow again, we limit the redshift, we get the colors, the 7-band magnitudes, we train a SOM with those colors, and then we color our SOM with photo Z and some physical parameter property, for example H-band magnitudes. Then we project the AGNs from EC catalog onto the SOM and see if different methods occupy different positions on the SOM and how much overlap they have. Okay, so let me restart and clear all the cells so that we can run this together. If this is the first time you're running the notebook, you can uncomment this pip install, which gets all the required libraries and things that you need to run this notebook. Here we are just, in addition to importing the needed libraries, we are also defining, for example, the redshift range that we are interested in, the signal-to-noise ratio, and some of the parameters that are set in the beginning, how many times to train, number of iterations, etc. where to cache the data, where the catalog data exists, and things like that. So simple setup in the beginning, and we are good to go. Okay, so as I mentioned, there are these three AGN FITS files that these papers that are in it all has already released together with a README file, and how they are selected. For example, there should be a flag there that is set to 1. There is a magnitude cut that is chosen for this for these AGNs, and there are different methods of selection of the AGNs, each of them really looking at different signatures in the galaxies to count them as an AGN. For example, some look at WISE color, some look at BPT diagrams, so spectroscopic emissions and broad emission features. Some of them use near-infrared colors, etc. And it is not super clear that whether these selections all select the same kind of population, or there are some overlap, and this is what we are going to test. Some of these selections are by default very similar. For example, the YC75 and R90 are just selecting two different reliability and completeness, and in this notebook we combine them together. Or for example, if two of the selections both use near infrared colors, we group them together. This is just to simplify the picture a bit. And some of them use random forest, some of them, random forest, some of them do an SED fitting, and if they are better fitted with an AGN SED, they are considered to be SED, to be an AGN, etc. So this is reading those FITS files and grouping the AGN selected selections into the groupings that I showed here, the 8 different groups that we have. Okay, and this is just showing you the number of AGNs combined in these 3 catalogs, and then if we do add the redshift cut, here are the numbers. Sorry, the redshift cut happens later, but these are divided into different selection techniques. Then not all those catalogs have redshifts in them already, so we need to query their redshift from the MER catalog, and also their photometry. Because querying the photometry is many bands and it takes longer, we first query for the redshift and then query the photometry for the subset. That is what is happening in this cell. Running it, and because I have previously run this, we are doing it faster here using the cache data. So if you run it once, the first time it takes longer, just leave it running and come back and then do the changes that you might need to the later cells. Okay, so here it is telling us that in this redshift bin, and with the criteria that we put on the 7-band photometry, how many sources we get about 4,800 AGNs in the north, about 10,000 in the south, how many of them have a SPECSI, etc. For building the reference galaxy sample, we put the same criteria on the magnitude so that we are not looking at fainter or brighter samples, and same redshift range. So doing that, so basically getting the photometry of a sample of about 50,000, and this is just to be relatively similar to the number of AGNs that we have. And because this is a large number, it will take a bit long to query them. And here I've only queried from EDF South, and we check later in the notebook whether there is a field-to-field difference from north to south when we map the AGNs on the same SOM grid. Okay. So nothing major, we are just comparing the training galaxies with the AGN candidates and looking at their colors before getting to the sum. The underlying gray distribution is the reference galaxy from G minus R all the way to J minus H, and the histograms in black show the AGN sample that are plotted on top. And here you can already see that we are looking at redder AGNs compared to the reference sample, specifically in the near, more so in the near infrared. Now we get to training the sum. We use the package called minisum, and just to briefly say what the sum does, it's an unsupervised dimensionality reduction technique that learns the distribution of colors in high dimensions, so here in our case 7 dimensions, and project that onto a 2-dimensional grid. And the idea is that topology is preserved with self-organizing maps, so if 2 galaxies are neighbors in higher dimension, in 7 dimension, then they'll be neighbors in 2 dimensions. And this is just a way of grouping things that are similar onto 2D space without losing all the information from 7-band colors. So if you are used to looking at color diagrams, this is just putting 1, 2, 3, 4, 5 color diagrams next to each other onto one 2-dimensional space. Okay, so we are here training the sum on 28,000 Euclid galaxies, and as you saw, minisum is super quick. If you use a package like SumPy, it will take slightly longer, but we get more or less the same kind of performance from both. Here I am showing the self-organizing map color-coded by photometric redshift going from 1.3 to 1.8, and you see more or less smooth transition, meaning that color has information about photometric redshift. And here I'm just showing the observed H-band median, and again you see brighter things here going to fainter in this corner here. Now we can project our AGNs onto the sum, and you can read all the details of the code. I am not going to make this video too long, but here's basically what we get. So if we map all the AGNs from all 3 different fields onto the sum, here is where they sit. So green crosses show the cells that have an AGN. Almost all of the cells contain AGNs, but if we do a density of points, then you see that some parts have less AGNs and some parts are very more AGN heavy. For instance, the brighter parts of the sum have quite many more AGNs in them, as expected. And if we do the same exercise but do it field by field, Euclid deep field north, Euclid deep field fornax here, and Euclid deep field south, you'll see that more or less the pattern is the same, but we have just less number of galaxies, so you'll see slightly different distribution, but more or less the same kind of story when we are mapping all the AGNs together. Now we can go ahead and ask what if I want to compare different selection methods, and that's the basically meat of this notebook. So if we do that, then you'll see how different selections compare. For example, if you use near infrared colors to select your AGNs, then you are not only looking for the most massive, brightest objects. If you choose WISE as your selection of AGN, then you are really looking at the brightest of things. And then there are different techniques that you can see what they are most sensitive to. For example, the random forest also is covering some of the bright things that WISE is missing, for example, here. And then we do again this same exercise, but a split into the 3 different fields. And the idea here is to show that even though the initial filters were slightly different in the north, in the south, and in the fornax, We are still mapping more or less onto the same places on the sum because the differences and uncertainties are statistically washed. So if you compare, for example, y's from the north here with y's from the south, you'll see that more or less they are similar in where on the sum the locus is located. So that is the idea of this notebook, and then we can go ahead and query spectra of each and just show 5 of them and see whether we do see the broad line H alpha in the AGNs, and some of them do show it, some of them don't. It can be issues with Q1 spectra, so better spectra to come in DR1. Then what we do later in the notebook is to go to SPE, which does line measurement for Euclid Q1, and query both for the control sample and for the AGNs their H alpha measurement, and try to compare them. So if we compare the H alpha luminosity of AGN sample to the control sample, you can see that there's only a very small offset for the AGNs, and we don't really see a huge difference, at least in this sample. Again, bear in mind that the quality of the spectra will improve substantially, and here I'm showing the control sample, the mean SPE H alpha, and here where the AGNs sit and their H alpha luminosity. So more or less a smooth. You can't really see a very H alpha dependent sum, which tells us two things. One, this is a bit expected because the shape of the SED, the filters are broad. They don't have necessarily too much information about H alpha, but you at least expect a bit of correlation with brightness maybe. And same thing here. And trying to push this a bit further so that we have a complete notebook for later with better data. We are here looking at mean H alpha luminosity, mean H alpha equivalent width, and the detection fraction. And the top row here is for the control sample. The bottom row is for the AGN sample. It's hard to see really trends here, maybe except for these two parts with elevated H alpha detection fraction in the AGN compared to the control sample, but a bit harder to see it here maybe. So that's all that this notebook shows. We got an AGN sample that is already published with Q1 data, and we use products from Euclid Q1, from the MER catalogs and images to CRS spectra and SPE measurements of lines, and we basically showcase the science use case with these data. All the details of how the ADQL is written, how the spectra are queried, how a SPE is queried, you can read both in this notebook and watch again in the previous videos that talk specifically about the data. I hope this was useful.